Okay, this is lesson 11, and it's sort of a continuation of lesson 10. I decided to make it a different lesson so that it wouldn't seem quite so long. 10 was long enough as it was. So if you notice, the first part of it says review of lesson 10, and what I've done is I've gone ahead and drawn on the board the phase diagram. Notice that I have drawn it in terms of resistance and reactance and impedance. And I had mentioned this in the last lesson. Since all of these are proportional to voltage, because we have voltage is current times each of these, that instead of drawing them in terms of voltages, we can actually just draw them in terms of resistance and reactance. And sometimes in a problem, that's what you're given to begin with, and then you can go ahead and draw the phasor diagram. Now, in step 2, it says to draw the phasor diagram that you had in lesson 11. Draw it reasonably to scale. Now, if you would like to draw it to scale exactly with a ruler, that's fine. It doesn't need to be quite that accurate, but it should be fairly representative. And the resistance the values that you had in lesson 10, the resistance was about 100 ohms. The reactance for the capacitor was just a little less, and the reactance for the inductor was I had calculated it as 320 ohms. So what I've drawn here is the resistor and the capacitor, reactance for the capacitor, approximately the same length, and then the reactance for the inductor quite a bit longer. And then we wanted to do the vector addition, so we moved the reactance for the capacitor up here, brings it back to here. This is, which I should have labeled, this part here is XL minus XC. So we do the vector addition, Pythagorean theorem. We have r squared plus this side squared equals the hypotenuse squared, and I have the equation for that over here. We'll use that in just a minute. Also, for the angle, the phase angle, we have tangent is the vertical over the horizontal. So I have that equation here as well. So in this phasor diagram, we're going to look at what happens to the various quantities as we change the frequency. So I have a bunch of questions on the top of page 96. We'll look through those somewhat briefly. So if we have the reactance, and if we change the frequency, and I've chosen, based on the way that I wrote the experiment, I've chosen to look at what happens if the frequency decreases. Remember that omega is 2 pi f, so the frequency is sort of built into the omega. So if the frequency decreases, and a lot of times instead of using words, I like to use arrows or symbols so that I don't have to write so much. So a slanted arrow down means decrease. If the frequency decreases, then we see that a smaller number in the denominator means a larger overall number, so our reactance will increase. If we do the same thing for the reactance for the inductor, if the frequency decreases, then the reactance of the inductor will decrease. I got my increase and decrease mixed up. Okay? So then the question is, well, what does that have to do with anything? Well, we notice that XC and XL are in 2 of our major equations, the one for impedance and the one for the phase angle. So if we're going to look at the quantity XL, let me get a different color here. We're going to look at the quantity XL minus XC. And as the frequency decreases, in both of these cases, XC increases and XL decreases. So if XC decreases and XL increases, then you can see that these two numbers get closer together. So this quantity actually decreases. The phase angle would be the same thing because it's XL minus XC, and the impedance would do the same thing. Since the XL minus XC is in both of these, we look at this term first, and then as a result of that, that tells us that the impedance decreases and the numerator decreases, and of course that tells you that the angle decreases. Okay? So we think, well, that can decrease, but it can only decrease to 0, and then if things keep going, then we will end up with XC changing more, and we'll actually end up with a negative number here. So what we want to do when XL equals XC, that is a particular case, and that's called the resonant frequency. Now, there are some other questions on the next few pages that I'll let you answer. But the whole point of this is impedance depends on the resistance, which we can't really get rid of, but it depends on the difference of XL and XC. And in one of the previous lessons, we found that the maximum current was the maximum voltage divided by the impedance. So in that case, if we want the maximum current, we have to have the smallest impedance, and that occurs when XL equals XC. So I'm going to erase some of this, and we're going to look at that condition. We're going to look at what happens when XL minus XC equals 0. Then, of course, XL equals XC, and XL is omega L, XC is 1 over omega C. We're interested in the frequency F, which is embedded in the omega, so we get omega squared is 1 over LC, or omega is 1 over the square root of LC. And then we also know that omega is 2 pi F. So if we're interested in this frequency, we'll end up with the frequency is omega divided by 2 pi. So that puts the 2 pi here, and we end up with 1 over 2 pi square root of LC. And this is what is called the resonant frequency. Now, there's a couple of other questions about the implication of the resonant frequency as far as what it tells you about the phase angle, and then how that's related to the power. And those questions, I think you should be able to figure out the answers to. So in our circuit, in our resistor, capacitor, and inductor circuit that we used in Lesson 10, we're going to try to figure out or determine the resonant frequency. And the first thing you're going to do is say, well, I can figure that out. I know what L is and I know what C is, so I will just put it in there and find the resonant frequency. Well, that is one of the questions, but first we're going to do this experimentally. So we have to figure out, what do we do experimentally? Well, back in this, if we have the XL minus XC equaling 0, then the impedance is just equal to the resistance. We might also look over here at our phasor diagram, and if XL equals XC, that means that our impedance is over here right on top of our resistance. And so from our equation that I mentioned earlier, I max is V max over impedance Z. But if we're looking at, let's say here, look at the voltage across the resistor. So as you vary XL or vary the frequency, XL and XC vary, and Z varies, and phi varies. So if you get to the point where Z is a minimum, that means that the phase angle is 0, you're going to get the largest current. And if you have been measuring or looking at the voltage across the resistor, this will tell you that the voltage across the resistor is a maximum. So what we want is the voltage across the resistor to be as large as possible. So what we're going to do is set up the circuit, and we're going to change the frequency. We're going to vary this frequency and watch what happens to the voltage across the resistor. And we don't need to know what the voltage is. We just need to know at which frequency do we get the largest voltage across the resistor. So I think this is basically what we have as theory. So Adrian's going to reposition the camera to our oscilloscope and circuit board, and then I'll show you what you're looking for. Okay, on page 98, down at the bottom, it says to draw an RLC circuit and show the V out across the resistor. So this is similar to the circuit you had in lesson 10. And if you left it set up from when you did lesson 10, you probably have everything just about right. The one exception, though, is we're going to measure the voltage across the resistor. And remember that I said the resistor, or whatever you measure the voltage across, must be in this position down here next to the ground. So I'm actually going to take this off. Make sure that you see what you're supposed to see here. So we go from the function generator, the ground part of it, to the circuit board. Anywhere over here is fine. We're going to use the resistor, the same one that we had before, which was the 100 ohm, brown, black, brown. So we have it in, make sure that it's in the same row as the ground wire. Put it up here, the capacitor, and this is the bigger one, I think it's 224K. So make sure it's in the same row as the resistor. Put the other end up here, and the little coil, you only have one of those, so you don't have to worry about that one. Put it in the same row as the capacitor. Remember that the coil, the wire from the coil is a little bit bigger than the others, so you have to be a little bit more careful about getting it into the holes of the circuit board. So then the other end goes up here, and then you have another wire from that end back to the position over here for the function generator. Now, I think it tells you in here, it should tell you, yeah, it tells you where to set all of these things. But you want 10K, and the reason you want 10K is because since I already know where the resonant frequency is, we're going to put it there. And then we're going to put our variable or continuous dial for frequency clear around to the right at 1. We're going to decrease that. So we're essentially starting at 10K, 10 kilohertz, and we're going to vary the frequency down and watch what happens to the resistor as soon as voltage across the resistor as soon as I get this connected. The amplitude over here, it doesn't matter exactly where you have it. We're not really going to measure the amplitude, but I found that if I have it set about at the halfway mark, that's fine. And let's see, oh, and make sure that you have the function generator on the sine wave. I think that's where it was before, but if you moved it, make sure it's back to the sine wave. And on the oscilloscope, I have this set at 1/2 volt per division. And all these divisions are centimeters, so you can say 1/2 volt per centimeter if you like. And then the sweep time, I have it set at 2 milliseconds. Not 0.2, but 2. And I'll show you why I chose that in just a minute. Okay, so I'm going to hook back the probe. The alligator clip goes to the ground. You could put it here, but I'm deciding to put it up here so it's a little more obvious that we're measuring the voltage across the resistor. And then the hook goes on the other side of the resistor. So we have this. Now, you notice that we have just a green band there. We don't really see the actual waves. And let me show you a couple of things. If I make it a smaller time, then you can actually see the waves. But the point of what we're doing here is we want to observe the amplitude of the wave. And it's much easier if we have this where we can't really see all of these waves, where it looks just like a green band. So now I'm going to vary the frequency and watch carefully what happens to the height of this. So I'm going to make sure I'm not in the way. And I'm going to change the frequency, now not the amplitude, but the frequency that goes from 0.1 around to 1. I have it at 1. This other knob is on 10K, so it's at 10 kilohertz. So if I move this down, what do you notice about the height of the wave? Now you notice it's spreading out, but that's not what we're after. The height of the wave is getting a little bit taller. Okay, now notice there it was short, and here it's getting taller. And I might even move this one more. Okay, so this is, oh yeah, this is back to 2 milliseconds, which is what I said. So we have it there. If we lower the frequency, the amplitude increases, goes up, and now after a little while it starts going down. And you can actually see the waves there. But the important thing is that the amplitude, the height of that wave changed. So now I'm going to go back, turning it to the right. It's getting taller, taller, taller. Now it's getting shorter, shorter. So somewhere in between there, and if you kind of do this fast through here, it's a little more obvious. So somewhere, I would say somewhere in between there is about where the maximum height is. And that's the one measurement that you want, is the frequency at which this amplitude is the highest. So once you've kind of decided that, then you can get the orange meter, and I think I showed you this earlier. Maybe I'll do it again. I'm not going to measure the frequency because I don't want you to see what it is here. I want you to do it. Okay, wrong one. Okay, does that show? Oh, well, I don't have a number on there anyway, so that's okay. So you'll have the black in the common, the red in the one next to it, and the frequency is kind of in the lower right-hand region. Now, it does say 2K. You have to be careful that you don't confuse the frequency region with the resistor region because the numbers are the same. They're Ks and 2Ks. This started out at 10 kilohertz, going down to 1 kilohertz, and so somewhere in between there is the resonant frequency. So I have it set on 20 kilohertz, and that's probably what you're going to need. And then you just connect the leads across the from one side of the circuit to the other side of the circuit. And I don't know, you could connect it from here to here. It doesn't really matter as long as you've got it across the whole circuit. And then it should tell you, read what the frequency is. So since that is on 20 kilohertz, your number will be in kilohertz, so don't forget the kilo. That you will record on page 99, and then you'll do a calculation on page 100 to see what the frequency actually is. Now, if the resonant frequency that you find does not agree fairly well with the resonant frequency that you calculate, you might want to go back, set up the experiment again, and put it at the frequency that you calculate and see if that's reasonable for getting the maximum amplitude. Because there is a fairly wide range of values there, so it's just kind of your judgment as to when you have the maximum. So I think that's the end of the experiment, and again, if you have problems, you can call me and let me know.